Today we're going to talk about calculating the pH during a weak acid strong base titration. Just like when we were working with a strong acid strong base titration, the key to a weak acid strong base titration is to ask what is in the beaker or what is in that Erlenmeyer flask. That's going to determine the pH of your solution. And we can ask it at the same 4 times. We can ask what is in that flask before the titration begins, before the equivalence point, at the equivalence point, and after the equivalence point. So before the titration begins, what we have is a flask full of weak acid. And since it's a weak acid, a little bit of it will have dissociated. We'll need to carry out a weak acid ice table in order to calculate that pH. Before the equivalence point, but once the titration has begun, we're going to have turned some of that weak acid into a conjugate base. So what we're going to have in the flask is a solution containing a weak acid and its conjugate base. A weak acid and its conjugate base makes a buffer. At the equivalence point, we're going to have turned all of the weak acid into its conjugate base. And so the only chemical species in solution that should be determining the pH is that conjugate base. And then after the equivalence point, we're going to have excess strong base present in solution, and that's going to determine the pH. Yes, there is still a little bit of that conjugate base in solution, but a weak base is going to have a much lower impact on the pH than a strong base, and so it is the strong base that determines that pH. If we take a look at what this titration curve would be expected to look like, we're again starting out with a weak acid, so I'd expect the pH to be low to begin with. And then as you add the strong base, you're initially going to see a rise in the pH, but as soon as you have a reasonable quantity of acid and conjugate base present, we're entering the buffering region, and the pH change will slow. And then once you get to that equivalence point, again, you're going to be outside of the buffering region. The pH will change very rapidly as you add that base. And then it will flatten out as the excess strong base determines the pH of the solution. And if we take a closer look at that equivalence point, at the equivalence point, we've added equal amounts of the weak acid, or at least stoichiometric amounts, of the weak acid and the strong base. So there are no reactants left. All I have is water, which doesn't impact the pH, and a conjugate base. That is the conjugate base of a weak acid. It itself is a weak base. And so at the equivalence point, we're going to have a pH that is slightly basic. And so one way to tell whether you're titrating a strong acid or a weak acid is to look at the pH of your equivalence point. If the pH of the equivalence point is basic, you must have a weak acid present in solution. It's time to do the math. Let's calculate the pH before we add any base to a titration when I take 25 milliliters of 0.1 molar acetic acid and titrate that with 0.1 molar sodium hydroxide. So before any base is added, the only thing I have in solution is the acetic acid and water. And so at this moment in time, I have a equilibrium set up because I have a weak acid, and I can use an ice table. I have not changed the volume yet, so using concentration is very convenient. And so just like when we were solving weak acid problems before, in order to solve this problem, we're going to need to write our Ka expression and set that equal to the known value for the acid dissociation, a constant for acetic acid, which is 1.8 times 10 to the negative fifth. And with a dissociation constant of 1 times 10 to the negative fifth, it's pretty fair to say that x is going to be significantly less than 0.1, and so we can neglect it. And therefore, this problem is relatively easy to solve. And once I know the hydronium ion concentration, I can solve for the pH. Once I start adding sodium hydroxide, I need to start using a BCA table because the volume is changing, and so the molarities are changing just because of the added volume from the other solution, in addition to the chemical reaction that's going on. So start your BCA table, as we always do, with a balanced chemical equation. And in this case, because I have a strong base present, my reaction is going to go to completion. Whenever you have a strong acid or a strong base present, the reaction will go to completion. And so when I put in the moles, I can just use a limiting reactant problem to figure out what my moles will be after the reaction is complete in that flask. And we'll see that once this reaction has come to completion, I have both the weak acid and I have its conjugate base present in solution, which means I have a buffer. And so I can use the Henderson-Hasselbalch equation to solve for the pH. And remember, when you're using that equation, you can either use molarity or moles of your acid and conjugate base. And so once I've used that Henderson-Hasselbalch equation, knowing the Ka for acetic acid is 1.8 times 10 to the negative fifth, I can find my pKa and put the log of the base form over the acid form, and I can find my pH. You'll notice that the pH is a little more acidic than the pKa, which makes sense because I have a little more of the acid form present than I have the base form present in solution. If I continue to add sodium hydroxide, I can find the pH after 25 milliliters of base has been added. Again, since I'm in the middle of my titration, I'm going to use a BCA table. And I'll see when I look at the amount of moles of total acid and total base that have been in this beaker or in this flask, I have equal moles of acid and base. And since this is a 1-to-1 mole ratio, this corresponds to the equivalence point. So if I take a look at what I have at the equivalence point, the only thing I have present is the sodium acetate. Now, sodium is a spectator ion and it's not going to impact the pH of the solution. But acetate is a weak base because it's the conjugate base of a weak acid. So that is going to impact the pH of my solution. And I'm actually going to have to work a weak base equilibrium problem. And since it's just the acetate that is the weak base, that's the only part I'm going to write in what is now my new net ionic equation. Down here below, I did not do a net ionic equation initially, but I don't want that sodium in there to confuse things. And so when I look at this, this is a base. And so I need to find Kb. And I want to remind you that your weak base dissociation constant is related to the acid dissociation constant because Ka and Kb multiply together to give Kw. So Kb is just Kw over Ka. And so in this case, that is 5.56 times 10 to the negative 14th. When you're working these acid-base equilibrium problems, Kb is in terms of concentration, the concentration of products over reactants. So we do need to go back and turn this into an ice table with concentrations in it. And so the concentration of the acetate was the moles of the acetate that were present in solution divided by the now total volume of solution, which is 50 milliliters. Because there were 25 milliliters of acid, we've added 25 milliliters of base. And so I have my concentration of 0.050 molar acetate. That is then going to abstract a hydrogen and act as a hydrogen acceptor from the water. And in that process, it reforms a little bit of acetic acid and the hydroxide that's going to determine the pH of this solution. And because our Kb value is so tiny, 5.56 times 10 to the negative 14th, it's a very safe statement to say that the value of x is going to be much less than 0.05. And so we can neglect it. That'll allow us to solve for x, and therefore our pOH, and from there our pH. And we calculate a pH of 8.72, which you see is basic, as you would expect from having a conjugate base in solution. Lastly, if I keep adding additional base beyond the equivalence point, we are going to end up having excess base. And so at this point, what we have in solution is water, but sodium hydroxide and sodium acetate. Sodium hydroxide, being a strong base, is going to determine the pH rather than the weak base that is present in solution. And so we can just take that concentration of sodium hydroxide, since we know it will dissociate completely, that will be our concentration of the hydroxide ion, and from there we can find pOH and pH. You will notice that in every titration problem, whenever I got to a new volume of base, I went back to the question of what is in my beaker, and I'm always looking at total in sum, how much of each of the chemicals have I added at that moment in time. And that allows me to decide how to then solve the problem.